Let's get started with the last paper session of the conference, where the Haptics 2 session. Yeah, I'm the session chair, yeah, Yongjae Yu from Hanyang University, and welcome you and welcome to the Haptics 2 session. We have three papers based on the program book, and each of the presenter will present 12 minutes, and we have 3 minutes of the Q&A. And the first paper, now let's get started. And the first paper is the passive haptics role in VR-based ergonomic workplace assessment, presented by Robin Gritzel from Trier University.
Yes.
Let's welcome the presenter.
Yes, hello, my name is Robin, and originally I'm working at the Institute for Occupational Safety and Health of the German Social Accident Insurance, to keep this sure, but I'm also a PhD student at Trier University. Digital twins enable an early risk detection before even physical workstations exist or a mock-up exists. So the actual research about validity, especially for ergonomic risk assessment, about this task is uncertain. But for using real movement data from virtual environments, the key fact is that whether the movements measured in virtual environments adequately reflect, otherwise they have the risk of making the wrong design decisions. So with the help of virtual reality, we can bring digital twins of real workstations to life as early as the planning and design phase. This opens up possibilities for us because we can use measurement-based ergonomic assessments and can carry them out more flexibly, quickly, and cost-effectively. But the central question is, can ergonomic assessments from a virtual reality be validly transferred to real conditions? And this derives in our first research question, which is, do task-specific joint angles differ between real environment and virtual environment, and do they matter for ergonomic assessment? How are virtual environments used for ergonomic assessments today, or what are they proposing to us? A combination of virtual reality and motion capturing enables measurement-based methods in virtual environments, and this increases the objectivity of ergonomic assessments. Physical mock-ups can be replaced, and they are comparable for static or simple tasks. But the system fidelity influences the validity, and the lack of haptics leads to a limited movement accuracy in complex movements. What could be a possible solution? Real contact in virtual environments. So the use of passive haptics promotes us a realistic movement execution, enhances a sense of presence, perceived realism, and motor control, which leads to which impacts our ergonomic data. So our second research question is, do passive haptics influence the movements of the corresponding ergonomic assessment in virtual environment? Therefore, we've conducted a laboratory study. It was a within subject design where we compared the passive haptic setup, where there's a virtual environment and a real environment. We've had 9 standardized tasks with different load weights and a quasi-randomization via a Latin square. Our subjects have been 25 males between an age of 22 and 41 years old. 17 of them never used virtual reality, 7 rarely used virtual reality, and 1 occasionally used virtual reality. All the participants had to be physically active workers and thus are representative of many industrial activities. Our ergonomic analysis was done with a Coela methodology, and you can see here on the right side the real environment in the laboratory setup. The virtual environment was realized with precise dimensions using 3D models and tested and validated in preliminary studies, and the virtual environment had enabled collisions. The passive haptic environment was the combination of the real environment and the virtual environment. We are using the exact same objects as physical props, but they were untracked. We created the virtual test environment using the HTC Vive Pro 2 VR headset and the Unity development platform. We've used the Xsense Arvinda inertial measurement units for a full body mocap, and we placed particular emphasis on realistic and intuitive motion transmission. We decided not to use physical controllers in order to ensure natural hand movements, and instead we used the VR trackers on the forearms and used the live data from the motion capture suite to precisely transfer the test subject's hand movement to the virtual environment in real time. What are the tasks the participants had to do? There's a task which is named middle to low and middle to high task, where the participant has to move loads from a middle shelf to a high shelf and to a low shelf. You can see it on the GIF on the right side. And the load weight has been a cardboard box between 300 gram and 12 kilogram. The carrying load task was a task where the participants had to carry up a Euro container between 2.3 kilogram and 20 kilogram, carry it over a distance of 5 meters, and place it in a predefined target zone. For this talk, the important task is the repetitive loading task, because this will be the task which is shown in all 3 conditions. Here the participant has to move loads from a pallet into the shelf in a predefined order, and after placing all loads in the shelf, the participant has to move it back on the pallet. So let's take a closer look to the execution in real environment. Here you can see the participant taking the loads from the pallet, placing it in the upper shelf, in the middle shelf, on the lowest shelf, and after placing all loads in the shelf, he has to move them back from up to down, back on the pallet. So I think it's clear what is being done here. So in virtual environment, here you can see that the participant now is standing on the empty side of the measurement area and doing the task in a fully virtual environment. And now in the combined condition, the passive haptic condition, where the participant has been the visual stimulus only with the virtual with the HMD, but the props are in real, and he has to move them again from the pallet into the shelf and back from the shelf onto the pallet. What are the measured target values for our ergonomic parameters? We've measured the trunk inclination, the back torsion, the shoulder left and right elevation, and the knee left and right flexion. Why are we measuring those parameters? Because they are associated with lower back pain and are relevant for the occupational diseases in Germany. It's a Berufskrankheit in Germany. It's a disc-related disease of the lumbar spine, the osteoarthritis of the knee, and the rotator cuff lesion. If we are looking at the back region, we can see that compared to the real environment, in the fully virtual environment, we've had 6 differences, significant differences compared to the real environment. After we've used the passive haptics, all of these 6 differences had been eliminated. So we've gone from 6 to 0. If we are now looking at the results for the knee region, we've had initially 6 significant differences again, and using the passive haptics leads to an elimination of 3 differences, but it creates 1 new difference which has not been there in a fully virtual environment. So we've gone from 6 to 4 differences between compared to real environment. If you're looking at the shoulder region, the fully virtual environment was very perfect. It's only 1 significant difference compared to the real environment. And here the surprisingly happened that after using a passive haptic, we've had 16 new significant differences compared to the real environment, especially for tasks with high execution variability and particularly prone to an environmental variability. Many of the effects are significant, but mostly within a range of plus minus 10 degrees, so it is context or goal dependent if we can tolerate it or not. So from 1 difference, we are gone to 17 differences. Of course, we have to talk about the limitations of our study. The only male participant leads to unlimited generalizability, though that gender-specific differences in motor skills and muscle activity are not taken into account. Potential tracking inaccuracies, visual haptic disalignments, and lack of dynamic prop tracking are particularly relevant for tasks with high freedom of movement or close-up interactions. The lack of tactile or proprioceptive stimuli in the virtual environment, which only partially compensates for passive haptics, but multisensory feedback is crucial for the realistic motion control. Only the hands had been visible, so limited spatial perception and potential for better embodiment and more realistic movement through usage of full avatars. And only 4 specific movement tasks with complex fine motor or asymmetrical activities without complex fine motor or asymmetrical activities were examined. To conclude, the significant differences in movement patterns between real and virtual environment, especially in the upper body area, show their potential for the usage of virtual environments for the ergonomic risk assessment, but with limitations. Passive haptics reduce deviations, but can also create new ones. The deviations within 10 degrees are for the ergonomic assessment comparable, but nevertheless we need a systematic validation to check if all the risk assessment scores at the end will be the same. Improvement through additional sensory stimuli and more realistic object interaction is needed, and we should consider gender, age, and additional task types for a better generalizability. That's it. Thank you for your attention.
Thank you. We have time for a couple of questions. So questions from audience? While they are preparing, I'll give you a quick question about this. About your setting of the physical weight, there are some different setups, like 100 grams to the 20 kilo, if I remember correctly, right? Does any effects happen on the different weight of the load you related to the task?
Yes, that's part of the bigger investigation. It's a bigger study protocol. The participants has been 3 till 4 hours in our lab to do all the kind of stuff, more tasks that have been presented. So the influence of the weight is not investigated yet. We are still an ongoing investigation, so it's hard to say if there's an influence right now. They are different because we are using the empty weight of the loads. So the cardboard box has been 300 grams and the Euro container is empty, 2.3 kilogram. And then we've put loads into it to put up the weight. And we've done this because of the risk assessments. They should realize if the weight is higher, then the risk assessment score will be better, in our words. And that's the reason why we've put them so high.
All right, thank you. And another the subsequent question I have. Any questions from the audience before I'm having another question? All right, let me continue. And about the effect of the fatigue, like the 20 kilograms afterward, the participants might feel some, let's say, fatigue, kind of. So do you? I believe that you provided some let's say enough rest time between the sessions. But do you observe any, let's say, carryover effect before or after very heavy load, or yeah?
Yes, of course, it was very exhausting, and it was the summer days back in these days. It's very exhausting, but we've given them enough time to rest, and the inclusion criteria for the participant has been to be physically active workers, because we just wanted to have people who know how is it to work hard and to carry heavy weights.
Gotcha. Thank you. All right, we have still questions. Time for the one more question. Any audience? All right, it seems the questions is covered. So feel free to find the presenter if you have any question. All right, let's move on to the second paper. Please give a big hand to the first presenter.
Yeah, thanks a lot for the nice introduction. I'm very excited today to present to you our work, which appeared this year in the IEEE TVCG. And in this talk, I'll show you how we explore tangible haptic props as an alternative to traditional touch gesture-based interaction in handheld AR. Let's start with a short clip of IKEA's AR furnishing app, which lets you check if furniture fits into your home before you actually buy it. And while the basic placement you see here in the video works quite well, more complex and precise 3D manipulations can be surprisingly hard to perform on a flat touchscreen. Yeah, and as you can see here in the video, the problem is that we need to map 2D finger gestures to 3D manipulations. And this often requires remembering complex gesture sets and switching between modes. Also, your fingers can get in the way and occlude the object. And this is why we believe that haptic props as proxies could provide a much more direct and natural way of manipulation. And here you simply move or rotate a physical object in your hand, and the virtual one just follows. Yeah, and when you look at my desk, you will notice that it's filled with graspable objects, which probably also holds for all of your desks. And some of these objects on the table I even carry around with me all the time and every day, for example, my wallet or my keys. And our vision is that in the future, any of these everyday objects could instantly become a haptic prop, so automatically tracked by the smartphone and on the fly ready for interaction in AR. Yeah, to get there and to situate our contribution, let's briefly talk about related work, which has proposed many different gesture sets for 3D object manipulation in handheld AR. However, these gestures are often very complex, limited to 2 degrees of freedom at a time, and the fingers can also occlude the object that you want to manipulate. In contrast to that, there's a huge body of research on tangible user interfaces, but mainly for tabletops or fixed displays. And these works also investigated many different prop shapes, and their results show that props often feel more direct, more intuitive, and also often outperform touch in terms of performance, engagement, and learning efforts. However, despite this evidence, only a few works explored props in handheld AR, and those who did mostly looked at pen-shaped designs, and to our knowledge, none of them compared haptic props with touch for 3D object manipulation in handheld AR. So the central questions remain open. Do haptic props really outperform touch in handheld AR? And what role does the shape of the prop play in handheld AR? Yeah, and these are exactly the questions we set out to investigate. And as most of related works used image tracking for tracking the props, we also initially explored this approach in a technical feasibility study with 18 participants. So we 3D printed the cube, attached image targets to its 6 faces, and mapped its motion one-to-one to the virtual object. And for interaction, we added a simple hold-to-couple clutch. So holding the screen with the thumb links the prop to the virtual object, and releasing the thumb again unlinks the movement, and yeah, you can move your hand freely. And this lets users chain short motions for larger moves, perform fine rotations step by step, and also easily readjust the grip when needed. And we then compared this interaction to a common set of touch gestures. So here participants could translate objects with 1 finger and rotate them using 2-finger gestures. And participants completed a series of 3D docking tasks where they had to align a movable virtual object with a fixed target object until it snapped into place. Yeah, and while all participants successfully completed all docking tasks in both conditions, we also run into tracking issues. So meaning image-based tracking just wasn't robust enough for a fair comparison. But still, many participants preferred the prop for its intuitive and tactile feel, and almost everyone liked the idea of using everyday objects as props, which motivated us to continue this line of work. So for the main study with 20 participants, we removed the tracking limitations by using an OptiTrack motion capture system, relying on 20 cameras and active OptiTrack tags for tracking the props. And this allowed us to simulate a perfect tracking scenario and investigate the real potential of props under near ideal conditions. Yeah, participants solved 2 different kinds of docking tasks in this main study. The first was a 2D docking task, and here the virtual object were placed directly on the table surface. So participants had only to slide them along or across the plane and rotate them around the vertical axis. We also tested 2 accuracy thresholds, so one that required very precise alignment and another one that allowed a bit more tolerance. The second task was a 3D docking task with the objects floating in mid-air, and this meant participants had to use the full 6 degrees of freedom of translation and rotation. And again, we tested both a precise and a more tolerant threshold. And finally, beyond the cube we already had used in the feasibility study, we added 2 more shapes to investigate whether the shape of the prop makes a difference. So we added the rhombic cuboctahedron, or rhombi for short, and also a sphere. And we chose these shapes as they built on prior work and also span different degrees of roundness while still being similar in size and easily graspable. Yeah, with this study, we evaluated the techniques across several dimensions. So we assessed performance based on task completion time. We also measured workload using the NASA task load index. For user experience, we used the user experience questionnaire, preference rankings, and a concluding interview. And finally, we also analyzed movement patterns by clustering the trajectories of the phone and the virtual objects. For time reasons, however, I won't dive into the movement patterns or the UEQ scores here, but if you're curious, I want to, of course, recommend reading our paper, which has the full story. Yeah, let's start with the results, and we'll first look at performance, and here you can see the task completion times for the 2D task. So in the high accuracy condition, all 3 props were significantly faster than touch. However, in the low accuracy condition, we saw no differences between techniques, which indicates that simple planar placement is already well supported by touch. For the 3D task, however, the picture is much clearer. So for both high and low accuracy, all props significantly outperformed touch. And this is also in accordance with our interview, where participants said that for the 2D task, the touch gestures feel very familiar, making the task easy. In contrast, however, they also said that screen friction can limit precision, the mapping from 2D to 3D feels awkward, and mode switching is cumbersome, which explains the higher task completion times for the more complex tasks. With the haptic props, in contrast, participants highlighted that they could manipulate all 6 degrees of freedom simultaneously, and many described the interaction as much more intuitive and easier. Yeah, in terms of workload, the results show a very similar picture. So NASA TLX scores showed no difference for the 2D task, but clear differences for 3D. So overall, participants perceived less workload with the props compared to the touch-based interaction. Yeah, and this is also in line with what we heard in the interview, where participants said that the mapping of 2D interaction to 3D required high mental effort for touch. And they also mentioned that instead of switching modes, they often compensated by walking around the objects, which likely added to the higher perceived effort. And overall, they also expressed rather negative sentiments about touch, describing it as frustrating, annoying, or simply very difficult. Now, this pattern is also reflected in the subjective ranking scores, where 1 is best and 4 is worst. And as you can see, for the 2D task, there were no significant differences between touch and the props. However, for the 3D task, all props were ranked significantly better than touch. And interestingly, just as with all other quantitative measures, we didn't see any statistically significant differences between the props themselves. That said, participants still voiced clear individual preferences. So for the cube, the edges provided helpful orientation cues, and some appreciated that it could slide along the table surface or that it resembled the virtual objects. Others, however, found it uncomfortable to rotate or even uncomfortable to hold. The rhombic cube octahedron was often described as the best combination of cube and sphere. Participants valued its edge cues and sliding, and many said that it was the most comfortable to hold, with a good grip and easy rotations. However, a few still noted that it could feel very uncomfortable in the hand. The sphere was mainly valued for its smooth, stepless rotations, and several found it easy to hold, easy to move, and intuitive to use. The trade-offs were the lack of orientation cues, and for some, the fear of dropping it. Overall, however, participants emphasized that the differences between shapes are only very minimal. And this aligns with the lack of quantitative differences, of course, suggesting that the prop shape matters more for comfort and orientation than for actual performance gains. Yeah, with this, let's move on to the key implications that we can draw from our findings and what they mean for future work. So first, across the board, props outperform touch in 3D manipulation tasks, and also in the high accuracy 2D tasks. And this shows the potential for precise interaction. But of course, only if tracking quality is good enough. So key next step is to develop improved and more robust tracking solutions. Second, for simple tasks like low accuracy 2D manipulation, we saw no significant differences between touch and props. And this suggests that touch can still be a viable alternative in such cases. However, to better support touch for complex tasks, future work should explore interactive constraints such as handles, guides, or snapping mechanisms to reduce complexity. And third, although participants had strong subjective preferences, we found no measurable performance difference between prop shapes. And this suggests that shape may matter less for raw performance, but exploring a wide range of form factors and affordances could, of course, help to better understand comfort and individual preference. And finally, participants strongly agreed with our vision of using everyday objects as props, like the things we have seen lying around on my desk earlier. And we are convinced that supporting this would make handheld AR far more flexible and natural. And because of that, we hope to inspire future work on tracking arbitrary objects on the fly just with the phone, and also see a wide range of potential application areas such as exhibitions, for example, gaming, education, also interior design and architecture. Yeah, and with this, I'd like to conclude my talk. For more details on our work, please refer to our paper, and I will happily try to answer your questions and look forward to the discussion. Thanks a lot.
Thank you. We have time for a couple of questions.
Hi, thank you for the talk. Hopeng from Lancaster University. So I'm just curious, how do you so in the interface, how do you select the object to be manipulated?
Okay, yeah. So we excluded object selection from our study because we said, like, for selection, touch is just the best thing you can do. So we said, like, people will select via touch and then they will start interacting with the prop. So that's what why we decided to exclude selection from the study. Yeah.
Okay. My second question is, I guess here for the study, you still use kind of a controller-ish object because it's kind of fully tracked for kind of experimental study, right? And then, and how robust would you think the result can be applied kind of in the wild interaction? For example, as you mentioned, the image tracking, and also there's certain problems, for example, depending on daily objects. For example, if I'm holding a coffee mug and I will spit the coffee if I do a 6-off manipulation, right? So how how do you think of this result? Kind of?
Thanks a lot. That's a really cool question. I think it's twofold. So on the one side, we have the tracking. That just needs to be solved. So we need to find better tracking. But on the other side, so like during our study, we also laid a selection of objects on the table and let people say like what they think of these objects. And for example, the mug is one good example where people exactly said that, like, if I use a mug, I will spill my coffee. So this probably won't work. But surprisingly, for all the other objects, people were very like open and said, yeah, this could work. I could use a pen. I could use my wallet. I could use my keys. So we were a bit surprised that they were so open for like using all these objects. Because, for example, for the keys, I thought like it's not a rigid object. Like it moves in my hand. And maybe keys are not like very well suited for that. But still, like, participants were very like positive about that and said it will work. Yeah.
And I guess one of the future work would be kind of also look at how to bind the everyday object to actually use the controller.
Yeah,
it can
that's
be
a good
just
point.
You hold it. And then
Actually, there's like there was a demo at Kai 2022 where they had something similar. So here the idea was, for example, for train tickets, that you just hold it in your camera, tap on them, and then it's registered as like a opportunistic interface. And that's like how I could imagine it, like how it could work. Yeah.
Okay, thank you very much.
Thanks a lot. Yeah.
Yeah. Last question. All right.
Yeah, thank you for your talk. Great work. I was just wondering, because in the video, in your main study, did you force participants to hold the prop in front of the phone like they would need to with the camera? Because of the OptiTrack system, of course, room scale, you don't need that.
Yeah. That's a good point. Actually, we didn't do that because, like, in the feasibility study, this was a huge problem. You had to hold it into the camera, otherwise it wouldn't track. But we argue that probably in the future, like, you have very wide angle lenses in your phones, and then it's not like that needed that you really hold it in front of your prop, but you can also let the prop in front of your camera, but you can also hold it more to the side. So that's how we see it, like, in our vision. Yeah.
or we have the back camera maybe.
Or the back camera, yeah, that's like
makes
a
it
good,
easier.
good idea.
Thank
I
you.
think there is I remember one study where they actually combined 2 phones to create like the full tracking volume. So I think it's possible. Yeah.
Thanks.
All right, I expect here the wonderful another paper for in next year. All right, yeah, thank you for
Okay.
the presentation.
Thanks a lot.
Let's give it a
Yeah.
Okay, hello everyone, I'm Kai Han Wang, a master student from the School of Design, SASTEC. I'm glad to present our research work today, haptic ceiling, an encounter type overhead haptic interface in virtual reality. This paper collaborates with researchers Han Shi, Jun Yuchen, Xuesong Zhang, and it is advised by Professor Song Wujie. Firstly, let's think about when we are in a real room environment. We can feel the haptic feedback come from multiple spatial components, including the floor beneath us, walls around us, the furniture we move, and the ceiling above us. To recreate this haptic richness in VR, environmental haptic interfaces have gained attention for their ability to engage users with haptically rendered VR environments. Multiple works have been envisioned to enhance this user's haptic experience in VR room environment, with mostly focusing on the interactions with environmental elements, such as floors. For example, Elevate developed a workable plenary floor that dynamically changes elevation and texture in real time. Or walls, like Zoom walls use mobile props to provide haptic feedback for virtual wall and door in VR. And moving furniture, like Room Shift employed a group of robots to lift, move, and place furniture, facilitating the creation of a dynamic haptic environment. But let's think about, as another important component of room environment, what about the haptic feedback from the overhead interface in VR? Actually, the haptic feedback from the overhead interfaces has already shown significant potential in various VR scenarios, such as for entertainment, like touching the overhead treasure box in a VR game, or for training. For example, it can simulate a realist complete ceiling where pillars operate switches located on it. Or in the space design, which allows users to perceive and adjust the height and tilt angle of shelves or cabinet in a virtual room. Previous research has mostly focused on using overhead interfaces for displaying information or supporting interactions with hanging objects. For example, through AI propose a tangible user interface that allows users to throw objects to the overhanging surface. However, the direct touch interactions with the overhead haptic interfaces in VR remain insufficiently explored. As a result, the needs for the haptic interactions with these overhead interfaces are often replaced by visual feedback only. So in this paper, we aim to enable direct haptic interaction with various overhead interfaces in VR and explore users' perceptual capabilities in this context. To achieve our research goal, we proposed haptic ceiling, an encounter type OHI, which enables the user direct interaction with it. After developing the device, we conducted 3 user studies. Firstly, we conducted a JND study to determine the threshold for users in perceiving differences of height and tilt angle. Secondly, we conducted a visual haptic illusion to explore the interface's height and tilt angle can differ from the physical interface without causing users notice. And lastly, we explored users' realism and enjoyment perception when using haptic ceiling in 3 VR applications. This is our device, we call it haptic ceiling, and its hardware system utilized a parallel mechanical system. The main components including the outer frame, linear actuators, and the end effector. The software system ensures that the linear actuators drive the end effector accurately. The inverse dynamic calculation was conducted in Unity, and the result was sent to Arduino by serial communication. Then the linear actuators move corresponding steps to drive the end effector to reach the specified position and orientations. This is how the end effector works. It has 3 degrees of freedom, including 0 to 540 millimeters along the z-axis and angular motion from -30 to +30 around both x and y axis. Then we conducted the first user study to investigate the user's haptic perception threshold of haptic ceiling, including the vertical height perception and tilt angle perception around both x and y axes. The study followed the traditional one-up, two-down adaptive staircase method, and in each trail, participants were present with reference stimuli and test stimuli, which refer to height or tilt angle in our study. Participants touch haptic ceiling without visual feedback and time limitation, and then participants were asked to compare whether the two stimuli were same or different. As shown in the right figure, for the height GND test, 5 reference heights was predetermined. At the beginning, participants first experience a training phase to get familiar with our system, and then participants experience 2 heights in each trail, one reference height, and the other is 10 mm above or below the reference height, and the difference between the 2 heights changed based on participants' answer. One staircase finished after 5 reverse of the difference changing trend, and the experiment finished after 8 staircase runs was completed. Similarly, for the tilt angle GND test, 6 reference tilt angle was preset, and the test finished after 8 staircases. The results show perceptual threshold of height and tilt angle, offering design guidelines for setting control ranges that ensure distinguishable haptic cues. Besides, the GND values can be used to overcome the latency of physical movements, for it doesn't need to move when the difference in the height or tilt angles are less than the corresponding GND values. Based on the findings from Study 1, we designed the visual haptic illusion study, aimed to estimate the detection threshold for the virtual interface height and tilt angle relative to the physical one without causing users notice. For the height illusion, the virtual interface was higher than the physical one, and for the tilt angle illusion, the virtual plane's tilt angle was bigger than the physical one. As shown in the right figure, participants could observe the virtual plane in VR and touch it with their virtual hands. Through a retargeting technique, the real hand and the virtual hand would touch the plane at the same time. After touching, participants answered 2 questions. Firstly, about whether they noticed the difference between the virtual and the physical ceiling, and secondly, about participants' confidence rate about how they perceive the illusion. And total 100 physical virtual pairs was conducted. This threshold shows the range that physical plane could differ from the virtual plane without breaking users' illusion. Within this threshold, we can map subtle physical changes to a bigger range of virtual plane changes. And the result of this study gave us insight into developing future applications in VR. Finally, we conducted the third user study to understand the user's perception of realism and enjoyment when using haptic ceiling in VR applications. Particularly, we designed 3 applications, including treasure box touching game, Michelangelo painting, and man exploration. The result of Study 1 and Study 2 were applied to get the motion of haptic ceiling in terms of providing distinguishable haptic cues, reducing latency, and expanding the virtual motion range beyond the physical workspace. We let the participants experience the 2 conditions, visual only and visual plus haptic. After each condition and application, participants rate their realism and enjoyment on a 7-point Likert scale, and a semi-structured interview was conducted. As the result shows, the visual plus haptic condition was significantly better in terms of realism and enjoyment for all applications. During the interview, none of the participants reported noticing the difference between the virtual and physical OHI during the experiment. Participants also gave comments about experience. Like, with haptic ceiling, I felt like I was immersively experiencing the game rather than completing tasks machinally. So through this study, we better know that OHI have the potential to enhance user experience in future VR applications. We have tried our best to make this research complete, but we acknowledge there are still limitations. Firstly, the mechanical structure can be further improved. Currently, the linear actuators occupy a certain amount of space and cause latency. Future work could consider adopting other mechanisms, such as a cable-driven one, to achieve higher efficiency. And secondly, the user studies focus on static interaction and passive haptic feedback only. Future studies could involve dynamic interaction to better investigate users' perceptions. Thirdly, the OHI system was tested independently without integration into other environmental haptic systems. For future work, integrating haptic ceiling with other environmental interface like walls or locomotion floor could enable richer full-space environmental haptics in VR. So in conclusion, through 3 user studies, we show the potential of OHI to enhance users' experience in VR. That's all for my presentation. Thank you for your listening.
Yeah, questions from audience? Yeah, while the audience are preparing, that I will give a quick question about this. Let's say to touch the overhead like a ceiling, there are some ergonomics issues. Like we need to raise the arm, and that might require some let's say fatigue in the let's say the shoulder, right? So did you any observe some ergonomic issues while while the participants are using the haptic ceiling, the OHI?
For the user study one, like you mentioned, there are many joints of our arm. So we conducted the study separately. We have 5 reference height, so the arm has different lengths when they are touching. And the results show there is no significance between this reference height.
I mean I meant the if the participants raise their hands like 2 minutes, 3 minutes, it's like a punishment, not the enjoying. So yeah, how they assess if they are using their longer time exploration or using their shoulders.
Yes, that's true. For a long time, some participants will say a little bit tired, and every 30 minutes they will have a short break during the user experience. And for the applications, currently is all for the short time touch and the static haptic feedback.
Yeah, not a long time.
Yeah,
use,
not
right?
long time.
All right, thank you. And we have time for a couple of questions from audience. All right, thank you.
Thank you for the very interesting interface. I had just one question. When you tested how the participants were touching the ceiling, were they restricted to a certain type of movement, or were they free to touch it any way they wanted?
Yes, during the user study 1 and 2, the perception study, the participants were free to touch the whole plan, but they were asked to avoid touch the edge of the interface to avoid the haptic cues to affect their perception. Yes, thank you.
Thank you.
All right, other questions? All right, let me have the final question for you. In your perspective, what would be the best fun or the best promising application area of this ceiling?
For me, I think maybe for the entertainment or for the training. For example, currently it already have the applications, commercial applications that use the OHI for the VR game like the Mario, or for the training like the pilot training. The pilot needs to touch the OHI and touch the switch located on it. So I think for future work, the haptic feedback can improve these VR applications.
All right. Any other questions? All right. It seems that everything's good, and yeah. Then let's give a big hand to the presenter, and it's time to wrap up the session. Thank you for participating, and I hope you enjoyed all of the ISMAR program. All right. Thank you.